Okay, so let's learn some derived rules today. So modus tollens, hypothetical syllogism, repeat, contradiction, and disjunctive syllogism. So derived rules are the ones that we can prove using the non-derived rules in the system. There are things they're rules that, the ones we introduce anyway, are rules that you really want to memorize, just like the other rules, because they cut down the amount of work required very greatly. They're just like having really good tools for performing a task. And really, some of these rules get rid of 10 or 15 lines in a proof. So don't consider not committing them to memory. The truth is that derived rules don't allow you to do anything that can't be done with the basic rules, because after all, they're derived from the basic rules. But the point is that they just make your life a lot easier. Okay, so this book gives you several more derived rules than you really need to memorize, and so I'm only going to go over here the ones that I think are the most useful. So the first one is Modus Tollens, MT. We abbreviate it MT and call it Modus Tollens, even though for some reason we call Modus Ponens conditional elimination. We call Modus Tollens by its classical name. And Modus Tollens is really kind of the opposite in a certain way of Modus Ponens, where Modus Ponens conditional elimination says, if A then B, A therefore B. Modus Tollens runs it the other way. So if A then B, not B, therefore not A. So this rule from now on is one that you'll be able to appeal to in doing proofs, and it'll cut down the amount of work you have to do by quite a bit in some cases. It's very easy to prove as well. All you would do is simply, you can figure this out on your own, but all you would do is an indirect proof where you would hypothesize A and then derive a contradiction immediately. So here's a little proof involving modus tollens. So we have if P then Q, if Q then R, and and then we want to show that if not R, then not P. So we could easily show if P then R, right, by two applications of conditional elimination. But how do you show if not R, then not P? Well, in the past, you would have had to do some kind of negation elimination proof, because simply hypothesizing not R would not have done anything great for you. But here, because we have modus tollens, we can proceed that way. So we hypothesize not R for conditional elimination. Then we get not Q and then not P by two applications of modus tollens, right? So we have not R, and if Q then R, so if Q then R, not R, therefore not Q by modus tollens. And since we have not Q now, we have not P by 1 for modus tollens. Okay, and that makes quick work of that proof. So with the conditional introduction, we have if not R, then not P. Another rule that is handy sometimes, it's not the most important rule in the world because it doesn't save a huge amount of time, but it's useful. It's also a classical rule called Hypothetical Syllogism. Hypothetical Syllogism says that if you have if A then B and if B then C, then you have if A then C. It's clearly correct. You can easily prove this by conditional introduction, right? Just hypothesize A, two applications of conditional elimination, and you get C. In fact, we did that earlier when we did introduce the idea of conditional introduction. Okay, so with hypothetical syllogism and modus tollens, you can make quick work of a proof like this. So if P then Q and not S, R if and only if P, if T then not S, and we're asked to prove if R then not T. So nothing tricky here. We go ahead and hypothesize R for conditional introduction, right? So then our task becomes to derive not T. And what we can see now is that we have R if and only if P. So if we converted that by biconditional elimination into if R then P, then we'd have if R then P, and we'd have if P then Q and not S, right? So if R then P by biconditional elimination on 2, and then we can state using hypothetical syllogism R if R then Q and not S by 1 and 5. So if R then P, if P then Q and not S by hypothetical syllogism gives us if R then Q and not S. Since we have R, we have Q and not S by 4-6 conditional elimination. And, well, then where are we? All right, we have Q and not S. We could get either one of these, Q, and we can get not S. And we have if T then not S. Remember, what we're trying to get is not T. So suppose you grabbed not S by 7 and elimination, and then you have if T then not S and the negation of not S, which will give you not T by 3 and 8 and Modus Tollens. Okay, so that's saved us, say, maybe 5 or 6 lines using those two rules. If R then not T, 4 through 9 conditional introduction. Okay, so 2 very important, pretty straightforward rules. Another rule, kind of an odd rule, but one that you'll find quite useful as time goes by, is called the repeat rule. And the repeat rule just says that if you have some formula A on a line, you can repeat that formula anywhere else you like just by using the repeat rule. So if you have if P then Q on a line, and for some reason somewhere you need it again, just write it again by the repeat rule. That's all that says. We didn't have that rule before. You wouldn't have been allowed to do that. So what kind of proof could you use that for? Well, here's a funny proof. You wouldn't have been able to do this before without repeat. So assume P or T, and then prove if Q then P or T. Well, the obvious thing to do is hypothesize Q, right? But then what are you going to do? I mean, P or T is just sitting there, but you need to be able to write it below. And there's actually no rule prior to now that would allow you to write it below. So now you get to write it below. 1 by repeat, right? So we now know that if Q, then P or T. Another example. So Q and not Q, therefore S, the simplest sort of expression of a contradiction implies anything. Anything follows from a contradiction. Now this is one we could prove without the repeat rule. It's just that the repeat rule makes it quicker. Well, how are you going to get S? Well, for now we're going to have to get S by hypothesizing not S, and now what we want is a contradiction. So the repeat rule just allows you to repeat the contradiction. What would you have done without it? Well, you would have had to go through some kind of silly steps, right? You would have to break apart Q and not Q and then put it back together. So you don't have to do that using the repeat rule. This allows you to infer the negation of the hypothesis, and then finally S by 4 and negation, elimination, right? Okay, so that's 3 rules under our belt. Again, all 3 fairly straightforward, intuitive rules, easy to memorize, I think. Let's talk about the rule of contradiction. So the rule of contradiction allows you to simply write down anything you want if you've got a contradiction in your proof, what we were just talking about. So the contradiction rule states that if you have A and not A, any two formulas, somewhere in the proof, they have to be on separate lines, then you can write down B. Now, that's a very simple idea, but because we're so used to using contradictions with the negation introduction rule, it's easy to get these two rules confused. So it's important to realize here that the contradiction rule is not a hypothetical rule. It's a straightforward rule, and it's not one that you would typically be using if you're in the middle of a negation introduction. If you're in the middle of a negation introduction, the contradiction rule doesn't normally come into play. It can, but that's not the normal thinking you're going to be using. And the important point to see here is these have to be on two separate lines. So if you did have a contradiction in the form of a conjunction, you would have to break it apart to use the contradiction rule. So we just did this proof before, and now we can do it even more quickly with the contradiction rule. Right? We've got Q and not Q. We want S. Well, how are you going to prove that? Well, Q by one and elimination, not Q by one and elimination, therefore S by 2-3 contradiction. You cannot just do it by one contradiction. Okay, you have to use two lines. Right. So now we can do a proof that involves a few of our new rules. Fairly straightforward proof. So we have two hypotheses. If P, then T or Q. If T or Q, then not P. And we're supposed to derive if not P, then M. If you go ahead and look at this for a while, turn this off and see if you can figure out the relationships here. You've got two conditionals, and here we see the consequent of the first is identical to the antecedent of the second, and that's when hypothetical syllogism comes into play. So with 1 and 2 in hypothetical syllogism, we'd be able to write if P, then not P, if we wanted to. Do we want to? Well, we're supposed to derive M from not P. Ordinarily, what we would do is hypothesize not P. If we had not P, which is equivalent to P, of course, it looks like we could either get if P, then not P, or if we wanted to use Modus Tollens, we could get if not P, then P. Either way, we've got a contradiction on our hands, which is going to allow us to assert M. So let's go ahead and apply hypothetical syllogism. We get if P, then not P by 1, 2, hypothetical syllogism. And then if we take on the hypothesis, which we could have done earlier if we wanted to, as a rule, sometimes if you're seeing, into a proof, and you see that certain steps are going to be useful, it's good to get them out of the way prior to going to a hypothesis, because if you need them later, you'll have them, even if you've already dropped a line. So we have not P, and we could strip the negations if we wanted to, but we don't have to, because this is the negation of that. And since we now have a rule called Modus Tollens, we can just go 3-4 Modus Tollens, right? P, if P, then not P. Not P gives us not P by Modus Tollens, and therefore we can conclude M because we now have a contradiction. Again, this is a contradiction, not P, and not P is a contradiction. You don't have to remove the negations. So by 4-5 contradiction, we have M, and therefore we have if not P, then M. All right, so our last rule is disjunctive syllogism, another sort of rule known since antiquity. It's got a traditional name, and we use the abbreviation of the traditional name. If we know that A or B, and we know that not A, it follows that B. Similarly, if we know that A or B, and we know that not B, it follows that A. So this is a super powerful rule that you'll want to learn. And by learn, of course, I mean commit to memory. So let's go ahead and prove disjunctive syllogism before we use it. And we can bring in our contradiction rule to help us with this, though we don't strictly need it. So let's prove that if we have P or Q and not P, that we can infer Q. Now, of course, if we use disjunctive syllogism, this would be one step, right? We would just write Q by disjunctive syllogism, but we're not going to use it here. We're going to derive it. So how are we going to do that? Well, we're going to have to use disjunctive elimination here, disjunction elimination. So we'll just go ahead and show that if P, then Q, and then after that, we'll show that if Q, then Q, which, as you know, is trivial. So hypothesize P, we immediately get a contradiction. So by our contradiction rule, we can write 2, 3, contradiction. And therefore, we have if P, then Q. So we drop a line, and we just demonstrate if Q, then Q in the usual way. And drop another line, and we have demonstrated by the disjunctive syllogism rule by universal elimination 1, 5, and 7. Okay, so hopefully that's a proof that would have been very simple for you to do, and now you're entitled to use this rule forever and ever. Let's go ahead and apply it. Just a reminder here that that it's an extremely important rule to commit to memory, and it will sometimes allow us to avoid disjunction elimination proofs. Not that we need to avoid those, but they're somewhat tedious, as you know, and it's nice to be able to keep proofs short when we can. So let's prove this. A disjunction, and a disjunction that might be hairy, right? I mean, it's a disjunction of a conditional and another disjunction. And so it looks like looks like we might have to do 2 disjunction elimination steps here, which, as you've seen from the homework, can be really kind of annoying. So how would we go ahead and prove this? We're trying to prove a conditional. We're supposed to prove if P, then Q or R. And immediately, hopefully, you'll notice that we've got the same, we've got the second disjunct is equal to the consequent of the conclusion. So this might suggest an interesting approach for us. If we go ahead and say, okay, this is a conditional, so let's hypothesize P, because it's a conditional. Now we're going to show Q or R. Now, it's not clear how we would do that right now. It's not clear that our 3 assumptions would yield Q or R in any simple or straightforward way. Might be able to do it with some very creative negation introduction work. But notice how we could just hypothesize. So this one was, of course, for conditional introduction. We could hypothesize the opposite of what we're trying to prove. So let's hypothesize it's not the case that Q or R. All right? Hypothesizing it's not the case that Q or R allows us immediately to apply disjunctive syllogism, and disjunctive syllogism gives us if P, then S. It's very easy, by the way, to get confused between disjunctive syllogism and modus tollens, right? So if modus tollens tells us that if A, then B, not B, therefore not A. Whereas disjunctive syllogism tells us A or B, in this case, not B, therefore A, right? So if you are not thinking clearly when you're doing a disjunctive syllogism, you might infer not A, thinking you're doing a modus tollens, right? So be very careful with that. So we have if P then S, and we also have P, right? So with P and if P then S, we can infer S, and there's our lovely little contradictions sitting there. And right now we are in the middle of a negation, introduction, proof, right? So we want that contradiction. So we got it, S and not S, by 2, 6, and introduction. And that allows us to assert the negation of our hypothesis, draw a line, which allows us to assert QRR by 8 in negation elimination. So we have if P, then QRR. Okay, so that's 5 new derived rules to commit to memory, and I'll give you a lot of practice on working with these as well.